All right, to start this video off, I want to go over this handout that I got in the class that I'm in. And there's some things that we deal with in this class on a regular basis. So there's some assumptions that are up here that aren't written down because we do this so often that we just know that f is a function that goes from a to b, and that K is a subset of that codomain B. And when you know the realm from which you're coming, you can now state that this thing is definitely equivalent to this thing. And why is that is actually not even the point of the handout. The handout is just talking about, notational things, how you want to handle this and how you can read the solutions. So what I wanted to do was cover this idea, this vocabulary terminology, the image of F, and the inverse image of that subset K. And I felt like this definition might be useful to me in the future. We don't use it in our class because, like I said, we use this notation and this concept so frequently that we don't even need to define it as being the image of F. But for the purposes of the video, I want to cover this idea. The image of F is the set of all outputs that F produces. So if I'm drawing my little clouds here that you maybe have seen your professors draw, this is what my cloud would look like. F goes from A to B, and I have this subset K, and this subset K is in the codomain. And so if I tell you that I have some f of x, there's my f of x, and that f of x is in K, here's my f of x, then what you know for sure is that there was some input that gave you that output. And that input is x. And normally you would even say, oh, well, I know that input is in A because that's my domain. Yes, but to accompany the idea of an image of F is this idea of an inverse image. And the inverse image, we are going to use this notation right here, F inverse. And I hear a lot of, people say it out loud, F to the -1, but that's not what it is. And it would be really handy for you if when you see it, you always just say the inverse of F. And here is the inverse of F of that subset K. And it has a definition too. It is called the inverse image, or pre-image. And it is created out of, here, ready? The set of all elements of the domain that map to the members of this subset K. So here I am saying that if you tell me that f of x is in this K, I am guaranteeing you that this x exists. And not only is it in A, but it is in this inverse image. And ready? It's stated very clearly right here. That f of x, here is my input, x, and the output that x creates is in my subset K. Then I'm guaranteeing you that there is some x, and that x is in the inverse image of that K. And that inverse image obviously is a subset of A. It's very easy to understand. This part over here where I have B and K is a subset hopefully is also familiar to you because you might recall that the codomain might not necessarily be the range. And I want to zoom in on this. So K is not necessarily all of the range. Okay, the range is definitely going to be the mappings of outputs. So maybe the range is all of this over here. This is my range. This is f of x. But K could be a subset of that. It could be a subset of that range. And I don't know, and I'm actually not even caring. And I will also remind you that because B is the codomain, there might be items over here if F is not onto, there might be items over here that never have an input. There's no input to these outputs. And if you're not, remembering immediately the famous example, I'm going to go over to it right now. Ready? I have this famous example, which is x squared. All right. And again, I have got f is a function going from a to b. And instead of using k this time, we're going to use L. And that's just for notational fluidity. We don't want you to freak out in class as a student. And I use another capital letter L. It's just basically, again, a subset of B. So I have my A and I have my B, and L is this subset right here inside of B. And I'm saying that I have my famous function f of x squared, which is not 1-to-1, and it is also not onto in this situation. If I wanted it to be onto, I would need to add a little plus sign right there, and then it would be onto. But for this particular point, I specifically want to pick something that isn't onto to illustrate an idea. And the idea that we're trying to illustrate is that we want to look at this L that we have right here, and we want to find 5 elements in L, but then we want to find this guy, and I'll talk about what he is in just a second, and he is only going to have 3 elements. So, ready? Here is my L. And I'm saying that I'm starting with 1, 2, 3, 4, 5 elements in L, and I'm drawing them very specifically because I want to fit this inside. F of F inverse of L. And I'm telling you right now that it is a subset of L. It is not as big as L. And here's why, because these 3 items are going to be in here. I started with 5 items, 1, 2, 3, 4, 5 items, and I'm going to end with these 3 items. And you're like, well, how do you do that? Well, how I do that is I'm going to take all of these elements from L, and I'm going to figure out what mapped them. Okay, so I have my F inverse. And these items that are in here, and I don't even know how many of them will there be. Will there be 3 of them? Will there be 5 of them? How many will there be in here? But I'm going to figure out what mapped these 5 elements that are in L. And then I am going to take these elements and I'm going to use F on them, right? I'm going to use F on them, and I'm going to find out how many elements I have left, and I'm going to know for sure that they land in this subset because they came from this input and they're going to go through my mapping function. All right. And I have it written down already. Here it is, the answer. What is L? L is going to be, ready? I have a -16, I have a -1, I have a 0, I have a 1 and a 3. And I'll show you some other alternatives here in a moment. But what I want you to know is that if you take a look at x squared, if you remember from, your math 2 teacher, your algebra 1 teacher, that the inverse of squaring something is taking the square root of it. And hopefully you remember that you can't take the square root of a negative. Wait, what? Yeah, in your class, you might recall that F inverse of x squared is going to be the square root of x. And you can't take the square root of -16. That's just, an imaginary number. And we are not in the realm of complex, so we can't do that. So L just immediately does not map those 2 negative numbers. And that's why I picked them. You could pick any negative numbers over here and they just aren't going to get mapped. And so when I look at my inverse, right? F inverse of L, the set L, what items do I get? Well, the square root of 0 is 0, and the square root of 1 is 1 and -1. Don't forget that. The square root of 1 is going to be positive and -1. And then here I have also 3, and I'm going to have positive and negative square root of 3. And that is my inverse set. And so, funny, it's kind of amusing to me anyway, I still have 5 items here. They just aren't the same 5 items that I started with. These guys never got mapped, and this guy gets mapped to those 2 different answers, and this guy gets mapped to those 2 different answers. And you might be saying, well, why is there a negative 1 here? Because if I squared a 1, then it could have been if I squared a 1, I get 1. And if I square a negative 1, I also get 1. So if I want to take the square root of just a regular positive 1, I don't know what I had started with. I might have started with a positive. I might have started with a negative. Now, here I have the obligation of actually running these inputs, because remember, this is inputs. I have to run these inputs through my output machine. My little function machine says to do what? It says to square them, and so I'm going to square them. 0 squared is 0. 1 squared is 1, and negative 1 squared is also just a 1. And then the square root of 3, when I square it, I get 3. And even if I take the negative 3 and I square it, I also get a 3. So there you go. And so to finish up, I just want to, I wrote these down for you guys. Need you to understand that we just covered an idea that the inverse image of a set does not have to be a function. Remember that this is just a set right here. And so we are doing the inverse image of a set. And it doesn't have to be a function because we're just trying to figure out how did we get the output set from the input set. An inverse image of a set is specifically allowed to send an input to 2 different outputs. And that didn't happen here, by the way. If you want to see an example of that, message me and I'll make a video, because I do have an example of that from a homework assignment. But also, you need to know that it's allowed, an inverse image is allowed to not map something that's technically in its domain. So an inverse starts over here at B, and it goes back to A. And so since B is, not necessarily the range, it's the codomain, there can be elements in there that don't get mapped, and that's allowed. So that pretty much finishes off this, example that helps you understand why what's in here in L could be bigger than what's in the output of the inverse image of L. So we want to go to a proof now about that, and that's for the next video.